Nope. It's gonna make a board presentation hard to see on Zoom if there's no camera. You're gonna do yours on the board also, right? Well, I think at least they'll follow your. I wonder if I could do like my laptop and the camera. It won't be great, but the camera, like my laptop, it will at least be there. So, or do you have? Okay. All right. Oh, I don't have a no. I don't have a PowerPoint. It's not going to last very long. Okay, I think we're just going to do it on the side camera, and at least the yeah, I think it's
I think there's a camera.
He might tell us the camera look like it's pointed this way. I can't tell.
Yeah, I think it is.
It looks like it is, but it's just we're not getting a picture. It's weird. Pick a button. Okay. So if nobody's watching on Zoom right now, but if anybody wants to watch after, there will not be video of the board, which is annoying. But maybe we'll keep the Zoom on just for the slides. We can share the screen and for the stuff you're doing, I think have some visuals for people on Zoom. Okay, so a couple of logistics, course logistics. You may have seen Amon and I've given you some amount of feedback, at least comment to everyone's proposals. Again, if you have any questions or want to run your ideas by us in person, I think that's the most effective way to get our feedback. So you may find our feedback just typing into the comments of the proposal was somewhat minimal. But those of you that have talked to me or Amon about your project, I think we have a much richer feedback to give in person with the back and forth. So if you do have doubts or questions or what have you about how your project is going to work, or you're running into problems you want help with, anything, please do come talk to us either after class or during office hours, or we can set up a time outside of those if any of those don't work. Okay, so that's the project. Oh yeah, also I'm going to release very soon a document, which is kind of like the guidelines for what you should put into your project report that you submit at the end of the class, and kind of some just suggestions on what to do in your presentation. Okay, so everyone, just a reminder, there's going to be a report and there's going to be a presentation, which is very short, like 5 minutes on the last day of class. That's when everything is going to be due on the last day of class. Just basically the report, you can imagine what we're looking for is basically a description of what you did. If there's any kind of math or kind of modeling that you need to explain just at least a high level, or if you read a paper, just explain how the method worked. Then tell us about your implementation maybe a little bit, and then your experiments that you ran and the results you got. So that's kind of the general thing we're looking for. So there's some pictures, I guess, at the end, maybe numbers, depending on what your experiments are. And then if you wrote any of your own code, submit that as well. And we're going to be very flexible on the format. You don't have to do Python notebook, but it could be a Python notebook. It could be a Word document, a PDF file, report, whatever kind of format, as long as you kind of cover everything you did. Yeah, and so that's basically what we'll be looking for. And again, I'll write up kind of what to make sure you include in your report, so that there's hopefully no questions there. And I think, I forgot the other announcement was, and this is an email I sent out today, that we set up a Ravana, not sure how you say that, group or account, I guess you call it an allocation of like time to run on the high performance computing system here at UVA. And really for people that are doing stuff that requires a GPU, just to make sure everyone has the computing resources they need to run training if you don't have a GPU or enough GPU time. I think it'll be plenty of time for everybody, but that being said, don't get all your 5 group members on there running it around the clock, from here to the end. We'll probably run out of hours. There's a limit, so just use what you need, and I think we'll be fine. But if you do need it, I have to add you manually, every person by their ID to the group. I think that's going to how this works. It doesn't automatically add the whole class, unfortunately. So send me an email and I'll add you to the Ravenna allocation. Okay, I think that was all the announcements. Any questions about anything? Okay, so now I have 4 minutes. I was going to take 15 minutes with our technical difficulties and announcements. There's only 4 minutes for me left, but I'll probably take a little bit more than that. But I'm going to just really quickly talk about the natural gradient. It's a pretty simple thing once we now have the Fisher information. It's an application of the Fisher information metric that we talked about. So just really quickly reviewing the Fisher information metric. As we talked about, there's kind of really 3 different equations you could write down that are all equivalent for the Fisher information metric, but I'll just write down the one that's going to be most important for us. And this is the information metric. It's going to be a positive definite matrix as a function of theta. Theta is the parameters of some probability model. Could be your weights in a neural network, which is what we're going to mostly be considering here for the natural gradient. And it looks like the expected value over the random variable that your probability distribution models of the square of the score function. Remember, the score function is the log likelihood, and take the gradient, where gradient here means treating theta as just a Euclidean vector with some dimension, however many parameters you have in your model. You take the Euclidean, the standard just gradient, derivative with respect to theta of each component of the log likelihood there, and you take that and you square it, which here means to take the gradient times its transpose. So if this is a d-dimensional vector, this is a d by d matrix. You have a d column vector times a d row vector, right? D by 1, 1 by d. The result is a d by d matrix. Okay. So yeah, so that was the Fisher information. The nice thing about not having the camera is I can just walk around and not worry about where the camera's pointing now. So this is nice. Yeah, so that's the Fisher information metric that we talked about. The again, this, remember, is like we said, a positive definite matrix, and we are treating it as a Riemannian metric on the theta parameter space, all the possible valid thetas. And the simplest case, we had the unit interval for Bernoulli. We turned that into a manifold with this metric. And then we have in problem number 1 in the homework, where we did the end of class last time, a Gaussian, a mean, and a variance is like the upper half plane, 2-dimensional plane. And then that is the space of valid thetas. And we turned that into a manifold, which is equivalent to a hyperbolic geometry. Those were the examples we did so far. But more generally speaking, this could be any model. You can turn your parameter space into a manifold. And now, as we talked about, I kind of preluded that the typical thing we want to do in machine learning or statistics, by the way, estimation, is learn the parameters of a model from a set of data, X. Notice this expected value is over the X, which is the data. And this is, of course, expected value means you integrate or sum over all possible values of X. In the real world, if our X are things like images, there's no way for us to imagine how to integrate over the space of all images. It's just not a tractable thing. So we would, if you wanted to compute this information metric for a much messier model than a Bernoulli or a Gaussian, very simple model, you would typically have to approximate this expected value with an empirical estimate from an actual observed data set. Okay, so how do I do that? Let's erase this really quickly. If I have a limited set of data, X data, I can get an empirical estimate to this expected value by just taking the mean of whatever's in here over the data I've observed. So if I have n data points, the mean is just going to be like the following: expected value of the gradient log likelihood. And I'm going to put in the X now. I was keeping the X out, but now let's have a data point Xi. Remember, the log likelihood is the PDF or PMF of the probability distribution we're doing with the log in there. And that depends on the parameter theta, and I'm evaluating it for just a single data point at a time here. And I can do it like so. Okay. So you're just taking you're computing this grad log likelihood, and for a single data point, and your current parameter is theta. If you want to estimate the information metric at the point theta, and you compute that gradient, you get this just a vector, and things a tangent vector at theta, and you take it kind of self-transpose. Okay. So that's the empirical estimate of the Fisher information. And now the last thing is we can do our typical probability model. We want to maximize the log likelihood. And so I want to move in the uphill gradient direction of the log likelihood. So this grad L is also the gradient I'm trying to move uphill in, but this is the Euclidean gradient. If I want to work under the gradient with respect to the Fisher information metric, that Riemannian metric, I need to take that into account. And that gradient, which I'll just write as grad L of theta, we were using, write out the word grad for the manifold gradient. I could maybe make it more clear if I put a little subscript there that I mean the gradient under this metric. It is going to be let me say it's equal, before approximating, it's equal to the Fisher information metric inverse times the Euclidean gradient L of theta. Okay. Very often you think of gradient vectors as row vectors, and you put this on the left. But if you think of grad as a column vector, you put it on the right. It's I is symmetric, so it doesn't matter if it's a row vector on this side or a column vector on that side. That's the equation. Okay, and where does this equation come from? It's thinking of theta in the Euclidean sense of theta as a coordinate system for the manifold. And it's a coordinate system for the manifold, and I of theta is a matrix in that coordinate system. And this is kind of the change of variables to convert a gradient in your manifold chart in the coordinate system to the actual gradient vector on the manifold. This is the equation. And that's what we call the natural gradient. Okay, and that's basically all there is to it. I mean, I could say a lot more about this, but I want to give Amon time to talk about diffusion models. Are there any questions about this? And yeah, to implement this, you basically would take something like a batch of data, some amount of data, enough data in each iteration of the gradient descent or gradient ascent, where you can get a pretty decent estimate of the Fisher information matrix at that point. You calculate the gradients for each point, and you do the multiplication like this, and you average it. And then the hard part of this computation, the reason it's probably not used for very sophisticated, very large models, I should say, is that you have to invert that matrix. So you have a lot of parameters, this matrix becomes unwieldy. You'll see if you do homework problem number 3, that this matrix is not too bad to invert if you have a logistic regression on like MNIST or some image set like that. Logistic regression is kind of like a single layer network. And this is not too hard to invert and do, and it does converge faster than taking a Euclidean gradient. And I'll make 2 connections really quickly, so then I'll stop talking, give them on the rest of the time. One is, if you remember, the Fisher information metric also looks like the expected value of the second derivative, the Hessian, right, or the negative of the Hessian. And if you've done any optimization, you know that taking like a Newton step is one in which you take the second derivative of the function you're trying to optimize, you multiply by the inverse of the second derivative times the gradient. And so this Fisher information is like a second derivative, and it's just kind of got this expected value over it. So this is very much like a Newton step, like a second derivative optimization. But because of this nice trick we saw that this is equivalent, you don't have to actually be able to need to be able to compute second derivatives of your log likelihood. You still can only stick to first derivatives. So it's a little bit more manageable for things that are hard to differentiate. It's still hard to deal with because of the inverse, though, but the second derivative you can avoid. The second connection I'll make is to the atom optimizer that many of you have probably, if you've done any machine learning neural network optimization, have probably used before. It's kind of the default standard, I would say, or variations of it, or kind of what people mostly use, at least in image models. And it does 2 things. One is momentum, which is not related to this. There's a momentum term that kind of smooths out the gradient over time. So each iteration you average with the previous gradient from the previous iteration. And that just kind of smooths out the gradient in over iterations. But then the second piece of it is very much related to the Fisher information. Essentially, what they do there is they take what is equivalent to the diagonal, an estimate of the diagonal of the Fisher information. And if I do that, then inverting is really easy. I don't have to really invert a matrix. A diagonal matrix, I just take 1 over the diagonal elements, and then I can multiply that by the gradient very easily. And so that's a much more efficient, but again, a looser approximation of the Fisher information that happens in the atom optimizer. Is kind of this, it's basically for each dimension of the gradient, you're deciding how fast to move per dimension instead of just keeping the step size the same across all dimensions. Let's see, I think that was all. Yeah, the thing I'll mention about the difference between Fisher information and the atom optimizer, if you have a function, let's say just a 2D theta that you're trying to optimize, and let's say the minimum's right here, if you have like level sets that look like this, then what you want to do is move faster kind of in this dimension and move slower in this dimension, right? And the second derivative tells you how to do that. The second derivative is steeper here, and if you invert, you'll move slower here, kind of faster here. If you move, because if you think about optimization, if I move too fast in like these kind of dimensions, I'll overshoot. If I move too slow in these dimensions, it's going to take me forever to get there. So this is kind of why you want to weight different dimensions differently. If you have kind of this anisotropic level sets, if you will. Now, the atom optimizer would work really great in this scenario. But if you had a scenario that looks like the following, where your level sets were not aligned, let's say, very well with the different dimensions, original coordinates, this is an off-diagonal, it's like the off-diagonal term in the Fisher information. And the Fisher information would scale this correctly, even if it's kind of like not aligned with the coordinate axes, whereas the atom optimizer would kind of have the same weights for these 2 coordinates and wouldn't actually improve this situation with the step sizes. So there is still an advantage to doing the full Fisher information in terms of convergence rate, but it may not be worth it if you have to invert a huge matrix. So it's kind of it's a trade-off that you're making, depending on what you're optimizing. Okay, I will stop there. Could talk a lot more about Fisher information, but any quick questions there before we transition to the next topic? Okay.
All right, so today we'll be like looking at diffusion models. I also have slides for this topic, and also because the camera is not working, I would urge you to open the slides. And for like anyone who's online can open the slides and sort of look at it while we talk about the topics there. You can use it for your own reference. We'll not really follow the slides exactly. I'll write stuff on the board as well, but you can refer it on the site because everything is there in the slides as well. So let me just sort of present it so that we have this as well. Okay, so diffusion models, essentially what we want to do is that train another type of a generative model. The two things that we want from a generative model, as we have discussed already, is that the generative model should capture the data distribution very accurately, and we should be able to sample from this data distribution effectively without repeating a lot of samples again and again. So what happens is that, let's say you have like a large amount of data. In this case, it's a bunch of images. And this data distribution is represented by this PD of X, which is a distribution from which you have sampled the data. So you just assume that the real world data distribution is sort of represented at PD of X. And what we want to do is that we want to train like a neural network model, which is parameterized by the parameters theta, which should be close enough to the data distribution that we have sampled the data from. So this is your real data, and this is the model that you want to learn. So here, what you want is that this model should be accurately describing the data distribution, and also that you should be able to sample from this model, which is very important because it doesn't really add too much value to learn a data distribution if you're not able to sample from it. Sampling from it means that if you are able to sort of accurately capture what the data distribution is, you should be able to sort of generate new data from it. And that is what a generative model essentially like aims to do. So once you sort of train an accurate enough p theta x model, you can then sample from it and generate new data. So that is what we're trying to do here. There are different types of generative models that have been that have like varying levels of success and have achieved different types of results and through the years. GANs were very famous before diffusion models came out. It was one of the more important and highly realistic generative models. It essentially works on based of a min-max type algorithm where the generator of the model is trying to fool the discriminator, whereas the discriminator is trying to predict if the new images that are generated by the generated are real or fake images. So based on these two models sort of optimizing the adversarial losses, you sort of optimize a model that can learn the data distribution. You can sample from it also. But we will here focus on diffusion models. And diffusion models have a very peculiar, unique structure where the model itself is only a denoising model or like an information addition model. Whereas, but if you sort of arrange it in a way where you create like a Markov chain of iterative denoising, you can create a structure where you can then use the same model again and again iteratively to generate new data. And let's see how you do that. Okay, so just for background, let me skip over the background. You can look at all of this material in the slides, and also we had like a variation not encoded class as well. So this is covered in detail already in one of the previous classes. So let me just skip over all the background. All right. So the denoising diffusion holistic model is the first model that sort of proposed this idea. You can look up this paper also as one of the first papers that started working. What we want to do is that a denoising process is made up of two distinct processes. The first process is the forward diffusion process. So you have a forward diffusion process, and the forward diffusion process aims to iteratively destroy data. Destroy information actually in the data. Okay. Whereas the reverse diffusion is incremental addition of data information. So it's incremental addition of information. right? And what do we mean by that? So in the forward diffusion process, what you will observe is that you have an image which is sampled from the real data distribution. You have like a real image, and then you slowly add a small amount of Gaussian noise to the image, which is just like by proxy reducing the amount of information that is present in that image. So you can perform any kind of transformation which is reversible, but is destroying some amount of information. So Gaussian noise is chosen to be that process because if you do this Gaussian addition several times, this has a closed form solution. So you can directly go from x naught to any time step. Like say, if you have like 1,000 steps of noise addition until you reach like complete noise, if you want to extract, let's say like the 500th step directly from the original step, because each of these steps are independently Gaussian steps, you can sort of compose all of them together and directly get the 500 step from the first image, right? So things like that are possible. It makes the modeling problem very easy, which is why additional Gaussian noise works very well. But there are other types of transformations also which sort of destroy data in the forward diffusion process. We are not really married to this Gaussian addition idea. What we can do is that you can come up with like any kind of transformation as long as it's destroying the information, it will work in this setting. All right, so let's look at the forward diffusion process in a little bit, like in further detail. So what we're doing is that given a data point x naught, you're adding some amount of noise to get a point x1, and you keep doing this until at let's say time x capital T, this is this noise, right? And this is your real data. Each of these steps is just Gaussian noise addition. And as I said that it has like a closed form solution, let's look at what the closed form solution is. So we are sort of representing this forward diffusion process as the distribution Q. So given an image, let's say at xt minus 1, which is any time step, if you want to generate the next time step, which is xt, right? This is just the distribution of one step of noise in the image, right? One step of forward diffusion is just taking xt minus 1 and predicting the next step. So it's just one step of what is happening. And that is just, you sample the image from a Gaussian distribution whose mean is just a shifted form of the original image, xt minus 1, and the standard deviation is this beta t factor. Right, now what are these beta t's here? Right, these are new terms that we have introduced. So depending on how intense you want to make this data destruction process, like if let's say you want to add like a large amount of noise in each step, like depending on how much noise you're adding in each step and what is the noise schedule of this information destruction, you change the values of beta to get like an appropriate schedule, right? So these beta parameters are only controlling the amount of noise that is added in each step, or in general, what the noise addition schedule of this forward diffusion process is. Okay, so these are sort of like parameters that we decide based on what kind of noise addition we want to do. Okay, another interesting thing here is that this is only for one step, but if you sort of compose all of these steps together, what you can do is that you can sort of extract any image from 1 to time step t, only given what the original image was, if you know all of these beta values, which we have set ourselves, so we know that is just a composition of these individual, oh, sorry. It's just a product of these individual steps one at a time. That makes sense? right? So if you want to go from let's say x naught to any arbitrary step x t, you can directly do that by just composing all of these individual transformations together. Okay, so now the reverse diffusion process. Well, so like the intuition behind this process is that if you keep like incrementally adding some amount of noise to the image, and eventually the image becomes complete noise, and you're able to reverse this process as well. Like you're able to remove a small amount of noise from the image to make it clearer. Like for example, if you can take an image like this and output like a slightly denoised version of that image, what you are doing is that you are sort of adding small amount of information into the image, right? Now imagine that you can do that incrementally starting from complete noise. So for example, if you start from this complete noise has no information and you sort of denoise the image a little bit, the model will sort of produce some semblance of an image with by adding like a little bit of information into that image based on what it has seen in the data distribution. And then if you do that iteratively, what you can do is that eventually you can find a real image which is completely a denoised version of pure noise. So you just started from noise, but you're able to recover like an actual image from the data distribution. And that is what you want from a generative model as well, that you should be able to just sample noise and be able to generate like an arbitrary amount of data just by denoising from noise, right? So that is the intuition behind trying to get this to work. So in the forward process, like we saw, is a very closed form solution to everything just being a noise addition. But in the reverse step, you'll see that we'll have some neural networks which will sort of simulate this denoising process. And when chained iteratively, they can then be used to sort of generate new data as well. Okay, so one step of denoising is what? Is just trying to predict xt minus 1 given xt, right? This is what we want to try to estimate, is just one step of denoising. This was one step of noising, which is predicting xt given xt minus 1. This is one step of denoising, which is given xt, any image here is trying to predict like a previous image, which has more information than that. We will do this using like a neural network. So let me parameterize this distribution by theta. So theta are the parameters of the neural network model that we'll use to do this. And this we just assume is that you can sort of model like a distribution whose mean is just predicted by a neural network model, which takes in the noised image and the time step at which the noising was done. So let's say the image is noised up to, let's say 500 steps. So you input 500 here, and you also give the model a noise version of the image. And then you ask the model to predict the previous xt minus 1 image, right? And this is just, we are assuming that this image, all of these images are just sampled from normal distributions, but the mean and the standard deviation of these normal distributions are predicted by neural network model. Okay, so the mean is predicted by taking the image xt and the time step, and the standard deviation similarly is also predicted by doing the same thing. So you take xt and the time step, and you predict the standard deviation, you predict this mean, and then based on this distribution, you just sample an image from it, and that image is supposed to be a denoised version of the noise image that you put into the model. That makes sense? So we want to just model this distribution, right? And we just assume that this distribution is a Gaussian distribution because all of the noise addition is also Gaussian, and also like the data, sort of you can make an assumption on the data of what kind of distribution it follows. So you just assume that this is a normal distribution, but the mean and the standard deviation of the distribution is predicted by neural network model, which is exactly where we would struggle to find what the mean would be. So you just plug in a neural network model and force it to predict a denoised version of the image. And because we can do the forward process in a closed form, like in a closed form way, we always know what a noised version of an image is. We always also know what a denoised version of the same image is. So you always have access during training, you always have access to xt and xt minus 1. And you can use that sort of tune this model theta. And then that way, once the model is trained, you can always just denoise an image. Okay. Right, that makes sense. So far, any questions about the forward diffusion or the reverse diffusion? Right, everybody following the intuition, right? All right. Okay, so now how do we sort of train this type of a system? The thing is that we understand that this type of denoising would eventually give you like a method to sort of generate data from noise. But how do we train a framework like this? Because there are multiple steps in the noising process, and if you do all of the steps together, then you have to sort of optimize on 1,000 different steps of noising at the same time, which is a very hard problem to solve. So there are different sort of ways to circumvent that by sort of training it only at one time step. But let's look at what the loss function is first and then go step by step and see how do we eventually train this model. So, okay. Like any other generative model that we have seen so far, here again, we want to maximize the negative log likelihood of the data given the parameters of the model. So we'll again use that objective function. We derive an objective function from there to sort of see how it works here. Right, so this is the negative log likelihood. It's just the negative log likelihood of the real data that you want to model. And in this case, we'll not look at the steps between these two steps, but what happens is that in this case, this negative log likelihood breaks down into three distinct terms. And each of these terms corresponds to a different step in the denoising process. So this step is the last step. This is L capital T. This is the information, like the Taylor divergence for computed for the last step of the noising process, which is just when the image has like complete noise and just one step before that. So this is the capital T step. For any steps between like the intermediate noising steps, except for the first step and the last step, is included in this middle term, which we'll see is the most important term because that is where most of your noising and denoising is happening. And this is just a discrete step, which is getting the probability of observing the real data, given like a slightly noise version of that same image. Right. So let me just write down that equation so that we can look at each term at a time. Right, so these are the three terms that we have in our loss function finally. Like this is just a simplified version of the negative log likelihood, and this we want to optimize on this. Like we want to minimize this quantity, and there are three distinct terms corresponding to each step in the denoising process. This is the last step. So what happens is that people observe that this value is very low compared to all of the other intermediate terms, and you will also notice that this is a discrete step. Like x naught is just a real image, and x1 is just a slightly noise version of that image. So because of it being like a fairly small value, because the first step of denoising will not add or remove that much information from the image, this step can be like safely considered to be zero. Like you can just ignore this time step, and that will not affect your optimization problem here, right? So you can, like in most papers, people just set this to zero and you can completely ignore that step. Okay. Another step that you can ignore is the first step as well. You'll notice that this does not really depend on our parameters at all. Like we do not really care about this term because it doesn't include the theta parameters, and that is what we are trying to optimize. So you can set this to 0 as well comfortably. Right. So out of the 3 terms that we had, the 2 that we did not understand can be set to 0 directly. And the one a term that we actually have to optimize on is a summation over all the intermediate time steps except for the first time step or the last time step. Okay, so it's just a summation over all time steps. And if you look at the term carefully, this is just a KL divergence between this tractable posterior distribution and this distribution, which is our neural model. That makes sense? Because this is just xt minus 1 given xt and x naught, which is the same as xt minus 1 given x naught, right? Because you can directly derive xt from x naught also given, because this has a closed form solution. I've written that both of these are given just to make this distribution look even simpler. But this is the same thing that we have here, and this has a closed form solution. So we know what this distribution is exactly, and it's completely tractable. So we have a tractable posterior, and the KL divergence of this tractable posterior is with the neural network model that we are trying to optimize, which is predicting xt minus 1 given xt. And this, again, as you see here, is just a normal distribution where the mean and the standard deviations are predicted by the 2 distinct neural network models. Okay, so the only loss function, like the only term in the loss function that we care about, has a tractable distribution, has a KL divergence between a tractable distribution and a distribution that is predicted by the model. And both of these are just normal distributions, and one of them we know exactly, the other one is being predicted by the model. Okay. Right. Again, at the bottom, you'll see that this, it says that this distribution, which is this, is a tractable posterior, and you can sort of write out the exact form of that distribution in terms of the noise schedule parameters that you've set. So the noise schedule parameters that you've set is beta t, where and these alphas are also in terms of beta t. So both of these alpha and betas are just like pre-decided values that we set to define what kind of noise schedule we will use in this diffusion model. So these are all known, like alpha and betas are all known. And this x2 is the original image, xt is what is given to you for predicting the mean. So this is a completely tractable posterior. So you can look at the exact details to see that you can directly find out what this distribution is. Okay. All right. So now that we know that the only term that we care about is the KL divergence, let's write out what it would look like. And it's essentially just a KL divergence between 2 normal distributions. So you know what it would be exactly. So let me just write down what it looks like. Okay, so this term here then becomes this estimate over Q. Right. So this term, the KL divergence term, like if you look up what the KL divergence is between 2 known distributions, and if you know both of those distributions, this KL divergence can reduce into like a direct mathematical quantity that you know. So for 2 Gaussian distributions, it's just difference like MSE between the means, and also a term with their standard deviations. Now, one more assumption that we make is that we just assume that the standard deviation is constant, right? So if you just assume that this is constant, this will cancel out in the tractable posterior, and also because it does not really depend on like it doesn't really have any parameters anymore, like because if you set it to constant, we don't really care about it anymore, right? Because what we care about is only to optimize these parameters theta, and if you make this term independent of theta, you don't really care about it at all. So what we're doing is just using one neural network to predict the mean of the distribution that we want to model. And we have the mean of the tractable distribution using the equation that we saw in the last slide here, right? So given these two values, you can directly optimize an MSE between the predicted mean from your model and what the mean should be. And that would give you a direct, very simple loss function that you can optimize on, train a model like this. Does that make sense? Yeah.
What is the intuition of having xt in the qxt minus 1 xt x naught? Like we have. Go for it.
Yeah, because if you have like the original image, and also a noise version of that image, you can recover any intermediate time step between that as well. So given what the first, given what we want to just do is this, right? Like xt minus 1. But if you also sort of pass in the information of x naught into that image, which can be recovered from xt also just by subtracting what amount of noise was added, it's easier to sort of compute xt minus 1 as a tractable solution, because the xt minus 1 here, the formula that we have written, you see is dependent on both x naught and xt. So you can sort of change this xt to write it in terms of x naught and only take x naught and also still predict this. But because this form is much easier, where you can just plug in x naught and xt both and it gives you what the mean is, it's easier to take in both as input and just predict that. Makes sense? Because if you know the noise schedule, we know that you can always recover xt from x naught. So you can just write what xt is in terms of x naught here, and that would also give you the same term. But just taking it as an input is just easier. Okay, so now we know how this is trained and what the objective function is, what the forward process or the reverse process is. Now we look at like a couple of tricks that people have sort of performed to make this training easier, right? To make this a little bit more easy to sort of optimize and and these tricks, a lot of these don't really make much sense. It's all of these things are just empirically found out in different papers, but it's nice to know them because all of the diffusion models now just work like that. So, all right, so, okay. So the reverse process, the neural network model here that we have looked at so far is a neural network model that is taking xt and is predicting xt minus 1. It's just one step of denoising, right? But imagine that you have a denoising model which takes in a noised image, but instead of predicting just a slightly denoised version of that image, predicts a completely clean image, right? It takes in, like for example, you have an image of something, let's say a dog, and then you add a bunch of noise to it, and you give it to, let's say, a neural network model, and the model just predicts the noise that was added to the image, right? And this is the prediction of the noise. Okay. So now what you can do is that, given this dog plus noise image, which is a noise version of the image, which is let's say xt, you can just subtract the noise prediction to get the original limit x naught. That makes sense? Because we know what the noise is, because we are adding the noise ourselves to this image. And then if we predict what noise the model thinks is added to the model, to the image, and if you compare both of these noises, then you can also sort of train like a denoising model, but the model, instead of denoising this image by one step, is completely denoising it, right? So what would happen in that case is that you would take an image like this, and instead of predicting x4, you would predict what x naught looks like directly. It won't be a very good prediction if the image is very highly noised. Like for example, if the image is noised up to this level, and you try to predict the original image will be very blurry. Like it won't be the best version of the original image. Like you can't really directly skip all of these diffusion steps to directly recover an original image. You have to do this iteratively to come up with a more realistic image, but it will still try to remove all the noise from the image. Okay, that makes sense. And why do we do that? Like if you, so let me ask you a question. Let's get some ideas here. So start doing that. Like if we train a neural network model instead of which instead of denoising the image by one step is directly denoising the image to X naught, how would we then sort of generate data from a model like this? Right? Because what will happen is that if you give it complete noise, it'll give you an original image, but the image will not look like anything. Like it would be a clean image, but it would not be as high resolution as it would be if you do this iteratively. So in that case, how do you now then sample from this model? Any ideas? Anything, just come up with something, Yeah.
Add a little noise and then
Reverse it again.
reverse.
Yes, that makes complete sense. So what you do is exactly that you take XT, you completely denoise it. You get an image which is completely clean, like you remove all the noise from it, and then you add like t-1 steps of noise again to the image. And then you denoise it completely, you get to X naught again, and then you add t-2 steps of noise to it. Right? And then you denoise it completely, you go back to X naught again, and then you add t-3 steps of noise to it. So that way, at each step, the model is completely removing the noise, but you're adding the noise back in so that you are able to simulate this iterative information addition process. Right? That makes sense? That's clear, right? Okay. Okay, so if you sort of design the neural network to be a noise prediction model like this, how does the loss change? Like how do we will have to change this loss, right? Because this loss is now predicting the mean, but we are not really predicting the mean from the model anymore. The model is now predicting the amount of noise that was added to the image. Okay, so how do we change the loss function to take this into account? So what you will observe is that if you replace all of these mean terms in terms of the noise and the original image, like in terms of how the original image sort of transforms, like this is XT, this is exactly what XT is, and this E theta is the neural network model, which is taking this image and is predicting the amount of noise that was added to the image. Okay, so this E theta, epsilon theta, sorry, this epsilon theta is the neural network model now. Instead of mu theta, we were predicting the mean before, right? Now, but we're predicting the amount of noise added to the image. And how are we predicting this? Is that we take in the image xt, which is a noise version of the image. We also take in the time step of how much noise was added to the image, and the model then predicts the noise that was added to the image. We also know what the noise is because we add it ourselves. So you just subtract the noise that you add to the noise from the noise that is predicted by the model, and this is just your loss function. Right. In this, you will see that there are a lot of these terms as well, but you can set all of this to 1. Okay, because you will see that none of this is dependent on the parameters that we're trying to optimize, so you can set the whole thing to just 1. And this is just for one step, right? So this is a reduction of this term, but only for one step. So if you just sum it over like all t-1 step instead of the first step and the last step, this will give you this overall quantity. But for one step of denoising, this is what you have to optimize. You just predict the amount of noise that was added to the image, and you subtract it from the noise that you predict that was added to the image, and then just optimize the parameters over this. Yeah.
So I have a question. The loss function you gave, just let me think about one thing. So, assuming we have an image, so we want to denoise it, and after we denoise it to the 0, then we denoise it again. It would go to the, I denote it as the -1. So according to your loss function, it just reveals that maybe when I go to the -1, the performance is not so good because the loss function here is, let me think about it, should be the same like the x1,
the first discrete
of the image.
Yeah, but you never go to time step -1 at all. you always operate between the first image, which is the real image, which is x naught, and a noise version of that image, which is between 0 and capital T, right? And you do that, like I said, by sort of repeating this process again and again. Like if you are at, let's say, x4, and you give this x4 image to the model, this E epsilon theta model, the model will predict the amount of noise that was added to the image. Let's say it predicts E hat, right? Now what you do is that you subtract this E hat from x4, right? And that would give you a prediction of what x naught would look like. Okay, because you've removed all the noise that the model thinks was added to this image after 4 time steps, and that would give you like a prediction of what x naught would look like the original image, right? And then you use the forward diffusion process again, which is a closed form process. Remember, it's a completely closed form process. So what you do again is that you're taking this x0 as the prediction from the model as x naught hat, and then you generate x3 again. So what you do is that you generate x3 hat as like x naught hat plus some amount of noise again, right? And this is like 2. So this is a different version of the noise because it's only worth 3 time steps now. So now you get like x3, like a prediction of x3, and then you put this x3 again back to this model, and the model will predict the noise, and then you go to x0, and then you add noise again to go to x2. So you always are operating between 0 and capital T only, but it's just like you keep going forward and backward, forward and backward. That makes sense? Okay. All right, so again, this is also talking about the fact that it's helpful that if you set this lambda t parameter to 1, the training becomes much simpler and it's easier to optimize in that case. Another thing that you have to notice is that this L simple, what we are doing is that we are also sampling a time step from a uniform distribution, because this is not simulating the entire forward diffusion cycle for an image. It's only sort of optimizing it for one time step at a time. So what you do is that let me just sort of show you the training process. And it'll be clearer if we look at the algorithm in the next slide. I think it's in the next slide. Yeah. Okay, so on the training side, the first step is that you sample x naught, and this is sampled from the real data distribution, which is q x naught, and this is what we're trying to model. So this is just real data. So you sample a real image. Okay. Second step is you sample a time step. And the time step can be anything between 0 and capital T, and this capital T is something that you decide. So if you want to make the diffusion process like 10,000 steps long, it will have like 10,000 steps of noise addition. So it's an arbitrarily decided value, which will tell you how long the diffusion process is. So you just sample a time step from a uniform distribution between the value 1 and whatever capital T is. So you just randomly pick one value from this, this sample T. And based on what that T is, you then sort of estimate, first you also sample some noise like this. So just sample some Gaussian noise from like a uniform distribution, which is 0 I distribution. So now we have like one image from the data set, and this could be like any real world image. You have sampled a time step, which is just to simulate this Gaussian diffusion process one step at a time. So you just randomly sample a time step t, let's say 300 or 400, or any intermediate step in the overall diffusion cycle. And then you sample some noise, which is just sampled from the Gaussian distribution. And then you do like a gradient descent step on this value, which is epsilon theta is the neural network model. It's taking a scaled version of the original image, and this scaling, what it does is that it converts the image into the xt image. So given x naught and these alpha values, what you are able to sort of recover is this is just equal to xt. Like this much. Okay. So what you do is that given this image that you have sampled and also a time step that you have now, you just add some amount of noise to this image, and that gives you the version of the image at time step t. Right? That makes sense? And then you subtract this from the noise that you sampled because we know what the noise was. You can just subtract it directly. Then you optimize on this value and take a gradient step on the parameter. Right? That makes sense? And because you're doing this one time step at a time, you don't have to simulate the entire diffusion process. And if you do it long enough, what will happen is that the model sort of will look at each of these intermediate time steps for different images and will automatically understand how it needs to deal with this noise and how to remove the noise from the image. Okay, and again, now for the sampling side, what you do is that you sort of first sample some noise, you and assume that this is the noise version of the image, like it's a completely noise version of the image. It's just pure noise that you've sampled. And then for each time step in the reverse diffusion process, which goes from capital T to 1, you again sample another latent code, which is also some noise. And then you apply this neural network model to predict the amount of noise that the model assumes that this xt image has in it. Right. So if the model is complete, like if you're at capital T, this will be pure noise, and this will just predict like some sort of a blurry image, and then you sort of compare that with the noise with the scale noise that you expect in that image, and then sort of you sample from that, and you keep assigning x t minus 1 again and repeat the process iteratively, like we discussed. Like you take some noise, sort of completely denoise it, and then add like almost the same amount of noise, but one time step less, and then denoise it, and then add one more time step less worth of noise, denoise it, keep doing it. And that way you will eventually be able to recover an image from the noise. All right. Okay, so now that we have seen how these fundamental diffusion models work, the problem with this is that we did not really look at any kind of conditioning in this diffusion model. So the diffusion model, once trained on a dataset, can randomly generate images from noise, but you will not be able to control what images it's generating, right? You can only feed in some noise and expect a real looking image from the diffusion model, but the image will not really is not really guaranteed to be consistent with any kind of information that you want in the image. Like if you train an image on, like, let's say a large number of dogs, it will start generating new images of dogs, which might not be in the data set, which are like real dogs, look like real dogs, but are synthetic dogs. But the model will still be limited to generating a random image of a dog without you being able to control what color of the dog you want, or what size of the dog you want, or even the species of the dog, because the model is not really conditioned on anything else. It's just randomly generating data. Okay, but it would be very helpful if we could condition this model on some of the parameters that we care about. So once you're able to control the diffusion process using a modality that we care about, this diffusion model becomes extremely powerful, where you can now generate any kind of image that you want, conditioned on the information that we care about, right? So if, let's say, we design a diffusion model to generate new images, what would be the conditioning signal that you would think would be the most informative for us to use to control this diffusion model? Right? What kind of a conditioning signal, like what type of a conditioning signal would you expect to be the most informative in the sense that we understand it the best, and the model also sort of, if it's able to understand that, we would have the most control over the denoising, like over the generative process of this model. Any guesses? Yeah.
It can be a lot of things, right? It can be text, it can be images, it can be.
Yeah, so it essentially, like, it can be any kind of information that you condition these diffusion models on, and the model will generate data which is related to the conditioning signal that you sort of give the model. But the most informative conditioning signal that people use is text directly, because we are talking in language, right? Like, I'm saying stuff to you in language. Any kind of information that we convey in this world is done through language. Okay, so if we are able to sort of directly manipulate the model and the generative process of the model using language, that would be the most powerful tool that you have to control the generation process of these models. Because language is intrinsically something that we compress information in, not images. Like, if you have like a lot of images, you can't really convey, I mean, you can convey like a scene or a feeling, but exact conveying of knowledge is always done through language, because it's the most compressed form of information transfer that we have as humans. So if we can sort of control this diffusion model using these captions, which are just text of anything, like you can describe anything in text, and if the model starts understanding that and starts generating images conditioned on that text, that would be a really powerful thing, right? So let's see how people have already sort of achieved this, and how it connects with the theory that we have sort of covered already. So overall, because we were modeling this distribution p theta, which is denoising the image a little bit, let me write it again. This is giving x t minus 1 given x t. What we want is that this denoising process should also take into account the conditioning signal that we want it to take into consideration while generating the image. So in addition to this image xt, we should also assume that the model should be able to handle like a conditioning signal and then denoise the image appropriately. So right, so in addition to being conditioned on the time step, like a noise version of the image, this model should also now be conditioned on a conditioning signal, which is what we will use to control the model. Okay. All right, so if you look at all the equations that we have derived so far, not much changes, in the sense that the reverse process is still a denoising process. What you're trying to do is that, given a noise version of the image, you're trying to predict how much noise was added to the image or what the previous time step would look like. So this p theta xt minus 1 given xt, and c is the conditioning signal. Sorry for the inconsistency, the c is the same as y, right? So this is the conditioning signal. So given this conditioning signal c, this distribution that we were trying to model, which is just a Gaussian distribution, which is made up of two neural networks which are predicting the mean and the standard deviation. These two neural networks, in addition to taking the noise image, the time step t, also now take in the conditioning signal c. Right, so nothing much changes in terms of the math or the loss function. The only thing that changes is that the neural networks that we were using to sort of predict this mean or the standard deviation also now are conditioned on the noise version of the image as well as the conditioning signal. Okay, so and the rest of it is pretty much the same. Everything, this distribution sort of shifts based on the conditioning signal as well, but we just trust the neural network model to figure that out also. You just give it the conditioning signal also, and just assume that the model will now sort of automatically generate conditional samples. And that happens because the training process enforces the model to agree with the caption, and the model automatically sort of figures out how it needs to use this conditioning information to sort of come up with images which are conditional on the information that you're providing. So All right, so let's continue from conditional diffusion models in next class. What we will look at is that we look at conditional diffusion models just in general. Then we look at several specific models that have come out in the last years, like the glide model that came out first by OpenAI. Then we'll look at DALI 2, just like the basic differences in these models and how sort of each one adds a new layer to the generative process. And then we'll also look at a specific application of this diffusion models in a setting so that we know how to use this, and you can sort of get a sense of how it's being applied in the practical world and can use it for your projects as well. All right, thank you everyone. Any questions about anything? All right.